anything unless you have finished all of the 1-1 assignments, because then you could go back and rating after the homework for this first 1, 2, 3, 4, 5 that we had were all from 1-1, those concepts. But again, let's just try to get used to doing that. After you do the homework, grab the yellow sheet and say, okay, now how do I feel about this? And I would say if it's just like one tough word problem that you can't do, that's a 3. That's if there's just the one worst word problem on the assignment that you can't do, you're still a 3 as you go through that. 1, 2 boatload of objectives here, and we didn't even really make it through the second one all the way. Or the first one, represent functions numerically, graphically, and algebraically. We're going to talk a little bit more about that today. Determine the domain implied in relevance. We did that, but then it says and range of the function. We didn't get there yet. So determine if a function is continuous or discontinuous, and the type of discontinuity. Is it removable? Is it non-removable? Is it a jump? Is it infinite? Is it whole? What is it? We'll talk about some of that today. Determine where a function is increasing, decreasing, or constant. Definitely my hope that we get there today. But we were looking at this section this morning and realizing 5 days it took us last year to get through everything here. And that was with skipping some of these domain problems. So we're going forward, but it's in little teeny pieces because there's a lot to cover here. So let's look at F, because F is a little bit different because it has 2 situations that we've been talking about as we go through this. And that would be, not only does it have a denominator, so we have to make sure that the denominator is not 0, but it also has a square root. So normally for square roots, we'd say, hey, whatever this is going to be greater than or equal to 0. But we can't do that with this one because it can't be 0. We have to make sure that 4 minus 17 is greater than 0 for the domain of this one. So then what do? Subtract the 4. Then what? And what does that remind us of from yesterday? You have to flip the sign. And we get that. Now, this has a name, so we're going to say domain of M is, and do our set builder. But this is an X this time. This is T. So I'm going to have to say T is defined as, and then I have T less than 4/7. So in interval notation, what's that going to look like? Write it down. Check with the chicken wing elbow partner. Let's see if everybody has the same stuff. Right? What's wrong with it? Well, why can't I include the 4/7? Because it would make it 0 in the denominator. Exactly. So we have to pay attention to the fact that this had 2 conditions in that denominator. Square roots, we think greater than or equal to 0, but can't be 0 because it is in the denominator. So that is an interesting little problem. And again, we can't. What I'm thinking is, if we get to the 5th day and we run out of stuff, I can come back and do some more of these. But I think I'm going to pick 3 off of this page that have some interesting things going on. And then we'll move on. That one has some interesting things going on. So, obviously with a square root up there, negative x has to be greater than or equal to 0. But like we just talked about with the last one, we would have to divide by a negative, which means things would get flipped around here. And then we do have a denominator. But that's not factorable. X squared plus 5. So I start thinking, the real issue is, when would that be 0? Well, that we can just solve. We can subtract 5 from both sides. Uh-oh. What's the problem? It's going to be imaginary. So what that tells us is there aren't any real numbers that we can't use down here. If they were, we would have found some, but these are going to be imaginary. This will be x equals plus or minus the square root of 5 pi. So that actually didn't produce any more restrictions for us. And the whole reason is, if you put positive or negative in here and you square it, you're getting a positive. So there's no restrictions down there for that denominator. We're not going to be able to get a 0 out of that. So our restrictions just come from the fact that we have square root in the numerator there. And this one didn't get a name again. Of course, they're all names. We could get used to that notation. But we're still using x. Oh, that's a really bad Richard. All right. Defined as, and we said x has to be less than or equal to 0. So, in interval notation, what's it going to look like? Here, what's that look like in interval notation? So include it. Yeah, we said less than or equal to. So negative infinity up to that 0 right there. So that one a little strange, but you know what, in a good way, because we didn't have any more restrictions thanks to that denominator. So if things come out to be imaginary, we know, well, those are not real restrictions, so we don't have to say anything about those. So that's kind of good. That saved us a little bit. J is kind of strange. Do we have any division by x? So we don't get any restrictions because there's a denominator. We have a square root. Is our x part of that square root? So this actually doesn't have any restrictions. Now, why would I pick this one if it doesn't have any restrictions? It's like, well, how do we write that? I mean, everything else has had a restriction. What do we do if we come across one and you could use whatever you want? Well, that's what we tell them. I mean, normally we wouldn't bother saying all real numbers because we would follow that up with, hey, but don't use this and don't use that. But this is everything. So in interval notation, do you remember what all real numbers looks like? Negative infinity to infinity, yep. There it is. So we needed to see at least one of those where there isn't any restrictions because the x is not under that square root. So we don't have to bother with that. And then Troy was asking about some interesting stuff that happens in both K and L, but I'm going to do L with you. Pretty obviously, we've got a square root. There's no division here, so we don't have to think about that, but we need this 4 minus x squared to be greater than or equal to 0. So right away, we move the 4 over. Divide by a negative 1. Flip the sign. And we need to take the square root. But here's where things change. Because as I look at this problem, I see, well, this was never meant for negative numbers. Because if you put anything in here, we're supposed to square it and it's supposed to be positive. So this is the point where we say, you know what? This is going to have to be absolute value. Is that too small? In order for this to work. Absolute value of x. We want to make sure that we're keeping things positive. And then that takes us back to what we did in the prereqs, where we say, okay, what does that really mean? If the absolute value of x is less than or equal to 2 and you're standing at 0 on the number line, you can reach out negative 2 this way and 2 this way. Because we're putting absolute value there, that takes that out. The absolute value is going to guarantee that that can be both of those.
How do we recognize whether we use absolute value or plus?
Right at this stage, right here, where you say, okay, I'm going to take the square root. If I'm going to take the square root of this, and it's an inequality, I'm going to lose something if I don't realize that this started by saying all of this is always going to be positive. It always will be. And so you have to go back to, like I said, those prereqs where you say, wait a minute, that means, anything between those is going to be good. So -2 is less than or equal to x, which is less than or equal to 2 is what we did in the prereqs. So we can write it that way. But what we're going to write with set builder notation is this piece. But for interval notation, there's an easier way to write that. So go ahead and write down what that would look like in interval notation. Use parentheses or square brackets. Square brackets. So again, it's all easier actually to write that with the interval notation. So another one to try if you want to do this. Again, if we end up with 5 days and then on the 5th day we run out of stuff to do, we can always come back and look at this one. But another thing to do, like it says, is verify on your calculator that what you're saying is actually where that domain is going to happen. So you punch it in and you see which x's is my calculator graphing as you go through there. So those were 3 interesting domain problems. Not necessarily difficult, the first 2 anyway. It's just that they're interesting and have different stuff going on. So now we want to look more at what happens when you graph these. I mean, the focus has been on domain, the inputs, the independent variable, all of that good stuff. But what about the range? Because you had some questions on the homework there from 17 to 20 that said, talk about the range of this data. To find the range of a function, look for all y coordinates that correspond to points on the graph. A good approach is to use graphical and algebraic approaches simultaneously. Keep in mind that in calculus, you're often not allowed to use a calculator to visualize the function. Throughout the year, you should be trying to get an idea of the shape of the graph before you grab your calculator. So, memory bank time. 2 over x. 2 over x. Yeah, it's a hyperbola. Anything with division gives us a hyperbola. And if we remember all of our algebra 2, we remember that the 2 on the top is responsible for pulling the graph away from 0, 0, from the origin. So what's going to happen here is that I'm going to end up with a nice little branch here and here. And that's because this is a positive 2. Now that might be enough for me to answer any questions they have about this. And if I've forgotten what it looks like, I can always plop it in the graphing calculator, or I could go ahead and make a table, and start to see what's going on. But I definitely need to know that that is hyperbolic, because when we divide, we're going to get hyperbolas, branches of a hyperbola. So now, solve graphically. Well, yeah, we'd probably give you a calculator, but just to show you you wouldn't need one. Let's just put a few points in here and see what's going on. So one of the first things I realize is I can't use 0 in here. So the domain of f, we have to leave x out. And I'm just going to really quickly not use set builder notation there just to show that we know that x can't be 0. So what we would want to do is just put numbers like 1 and 2 in for the right side, and -1 and -2 in for the left side, and get a look at it. What's it going to look like? So 2 divided by 1 is 2, and 2 divided by 2 is 1. So we've got 1, 2, and 2, 1. And there it is. Right, so, and then on the other side, if we put a -1 and a -2 in, we'll get -2 and -1. So -1, -2, and -2, -1. And it looks like so. And that's the division that tells us this is going to be hyperbolic. That's what we need to see. So, it says finding the range of the function, but yeah, I've also kind of talked about the domain as we've gone through. And what I would notice about this is I'm really using almost all the y's. This is going down forever, and this is going up forever. But there's just one number I can't use. And that's right here. It's here. Right there. It's never going to touch that. Never going to quite get there. So my range for f stands out would be, I'm just going to say, hey, y can't be 0. Everything else is good. But now that changes big time when we go to talk about interval notation, which is really what we want our answers in. So I realize this is going to negative infinity. I mean, it's going to keep going. That arrow is telling me that. But I can only go so far, and then I have to jump over that 0. So I'm going to go to 0, jump over it, and then back up again, thanks to that lovely arrow. So I'm going to show you a new thing. And this is something that'll, we're not going to ask you to confirm algebraically a whole lot, but this is something you're going to use in calculus. So how do we confirm that that is never going to be 0? We're saying that's never going to happen. That's what we're saying. So if we were to solve that, we could just multiply both sides by x. So this will say 2 equals, is 2 ever equal 0? Can't happen. So that's how we confirm algebraically that there's no way we are ever going to get 0 out of that. It just is not going to happen. What else did I have for notes here? Did you guys remember that was a hyperbola? Be honest with me. Did you? No? Okay. So it might be one of those things that as you're going through the homework, you might have to graph some of these on your calculator for a little while first before you remember, oh yeah, division is hyperbolas, and go through that. Because this is the only one we're going to do for range. I mean, range is generally something that either you graph it and you take a peek at it, or you just know because you know the shapes of the graphs. It's like knowing that absolute value graphs are always these. Knowing that anything that's a quadratic is going to be a parabola. You use that to your advantage and you just kind of visually figure out what's going to go on with that range. So if you've forgotten what they look like, put them in your graphing calculator for a little while and start coming back to you. Continuity. Continuity, one of the most important properties of most functions that model real-world behavior is that they are continuous. What does it mean to be continuous? It means as I draw the graph, my pen should never leave the paper. That's a continuous graph. If I am drawing my graph and there is a hole or a jump, something that causes me to pick that pencil or pen up and move to a different position, that's not continuous, it's called discontinuous. So if you can just get started and keep rolling and get the whole graph drawn, it's continuous. So this means that a function is continuous at a point if the graph doesn't come apart. Now we have to be, that's just doesn't seem like a real logical way to explain it, but there are jumps, there are holes, there are indefinite discontinuities that we have with graphs. And so what we have to do is just remember, hey, if there's a break in this graph, it is not continuous. So looking at a few examples with this one right here, the book never does arrows that time. We need the arrows there. And I realize if I put my pen here and I keep rolling with it, I'm never picking up that pen until I get to the other arrow. That's a continuous graph right there. So this is continuous over all x or at all x. This graph is continuous everywhere. Notice that the graph doesn't have any breaks. No jumps. This means that if we are studying the behavior of the function f for x values close to any particular real number a, we can be assured that the f of x values will be close to f of a. Oh my gosh, did I just make that sound? What it means is we're going to have some formula that we're going to use for this. And what we're hoping is for any x value that we choose, this x, when we put it in here, will give us this value. And if it's a continuous graph, that absolutely is going to happen. So that's what they're saying. They're saying your graph, your y values, should match. So if you look at that and you're thinking, okay, well, why wouldn't it? Well, what if there were a hole in this graph? And we had to graph that point right there. That's when it wouldn't be continuous. Because you'd have to stop and say, oh, wait a minute. Y doesn't equal f of a. It equals something totally different here. It's not along that graph. It's not smooth and continuous. So that's the reason they're getting into that kind of strange language with f of x and f of a. This little bugger right here, rats. You see the one spot where it's not continuous? Yeah, right here, right here. So we're going along just fine. Get to here. Uh-oh. For some reason, there's one point up there that just doesn't fit with the rest of that graph. So this graph is continuous everywhere except for this nice little hole right here. And if we're studying the behavior of this function f for x values close to a, we cannot be assured that as we put a into this function, we're going to get f of a, which would make it fit right here. Because for some reason with this graph, f of a just popped up in a totally different spot. So in this case, f of x is smaller than f of a. Notice that the y value here would be lower than this one. And this is called a removable discontinuity. Now it's removable because if we come along and say, you know what, this is ridiculous. This isn't f of a. I'm going to tell people this is f of a. I'm going to say it's right there and fill up that hole. And if I do that, then it is continuous. So that's a removable discontinuity, and it is called a hole. There is a way to plug the hole. We just mathematically need to tell people, put it right here. Don't put it in that weird spot up there. Put it right here. Now this graph, down here, also has a hole right there. And this graph also has a removable discontinuity. Because if we tell somebody the math to say, hey, at A, plug the hole with this, we could fill it. So if we're studying the behavior of this function, f for x values close to a, we're still not assured that f of x values will be close to f of a, because in this case, it doesn't even exist. There isn't anything there. There's no point. So for some reason, when they put a into this function, nothing came back out of it. But it is removable because we could tell people, hey, plug the hole for a, make y this. And we could make sure that that happens, and then it would be continuous because it would flow all the way through. So that's a removable discontinuity. Anything with a hole, we could plug the hole. This is not removable. We can plug a hole, but what we can't do is connect up two pieces that are not supposed to be connected, and that's what's happening here. So with this one, this is called a jump discontinuity. The graph actually goes from, well, an interval of y values to a totally different interval of y values. We're doing just fine, and we get here, and all of a sudden we got to lift the pencil and go up there. You know? So it is a discontinuity that's not removable. It is a jump discontinuity because there's more than just a hole at x equals a. There is actual jump in the function for the y values right there that makes that gap impossible for us to fill. There's no single point that we could define and say, yes, this is going to do it. And you'll notice, because these are supposed to be functions, if we did try to fill this hole, it would not be a function anymore. It would fail the vertical line. So there is no way for us to physically put those two pieces together without changing this from a function to a non-function. So a jump discontinuity. What we just did with the hyperbola earlier, this is an infinite discontinuity. There's absolutely no way to get those two branches to come together that would create a function out of this. Right now it's a function because it has an infinite discontinuity. Definitely not removable. The name for that is an asymptote. This would have a vertical asymptote at x equals a. remember vertical asymptotes? Never going to cross those. Never going to cross vertical asymptotes. So not removable. Can't do it. So some of your homework is just going to ask, what is this? What kind of discontinuity is this? Is it removable? And just have you go through and think about the fact that holes, yes, we can plug holes. But when there's gaps, we can't. There's no way to do that and keep this a function. So the key concept from these pictures is that we want the point x and its y value, f of x, to slide smoothly onto that next point, a, f of a, without missing it in either direction. So it doesn't matter whether or not you're drawing your graph from left to right or right to left. You shouldn't have to lift your pencil if there isn't some kind of discontinuity in there. So now a little bit here of language we started introducing you to in Algebra 2 when we talked about end behavior of graphs, but this is limit behavior from calculus. And this can be written using that limit notation. A function f is continuous at x equals a if the limit of f of x, so the limit of y, as x approaches a, fits right into what you know about the function. F of a. It just slides right in and things are nice. Otherwise, it's going to be discontinuous at x equals a. So obviously, we're going to spend some time, since it was part of our objective, talking about, do we have some points of discontinuity? Where are they? Is it removable? Is it non-removable? All that good stuff. So, identifying points of discontinuity. Judging from the graphs, which of the following figures shows functions that are discontinuous at x equals 2? And then are any of those discontinuities removable? So, we're looking for breaks at x equals 2, breaks in the graph. X equals 2, right there. Is that discontinuous? Yeah, it is. So judging which of the following show functions that are discontinuous, here's one right here. Now I want you to look down at the actual function algebraically. Why did that happen? It would make a 0 in our denominator. 2 minus 2 would be a 0. So that's why we have that vertical asymptote right there. And then it says removable or non-removable. What do you think? Now, this is an infinite discontinuity. This is non-removable. We're not just plugging a hole. It's nice. Alrighty, take a look at figure 1.17. Should I circle that because that's discontinuous? No, this one's continuous. That's just your average everyday parabola there. And if you're thinking, well, that doesn't look like a parabola equation down there, remember we could do FOIL on this and it would be x squared, so it would be a degree 2 polynomial. So that one's good. How about that third one there, figure 1.18? Should I circle that as discontinuous? Now with this one, I look at that equation that they have for it and I realize, yep, this is some good old Algebra 2 stuff here. Because if we factor that, we will see that the x minus 2's would cancel out. And if we can cancel that out, that in fact is removable. So what we would say is this is a removable discontinuity. And we think, okay, well, how could we tell somebody to plug the hole? Well, we could tell them that f of 2 needs to be 1, 2, 3, 4. If we do that, then they can come back and they can fill in that little hole. Because they'll know that, hey, if you put a 2 in this, you're supposed to get 4. And that would be removable. So one hole, not a big deal. But any kind of jump, and then it's not going to be removable. And again, when we talk about our asymptotes, those are definitely non-removable infinite discontinuities. So algebraically, discontinuities come from x values that result in division by 0. They make the denominator equal to 0. That's where we've always found our vertical asymptotes. If it's removable, it shows up as a hole in the graph. So that's if we can cancel it out. We look at the original and we say, hey, let's factor this, and this one cancels. That's removable. But if we can't get rid of it, it's never going to cancel out, as happened in this example right here. X plus 3 and x minus 2, there's no canceling there. That's not going to happen. Well, if it's not removable, it's a vertical asymptote. And that's going to be an infinite discontinuity. So this says use the equation to find the x values that make the denominator equal to 0. Then analyze what that same value does to the numerator. So they're saying if we put a 0 in the denominator, think about what number would make that happen and also put it in your numerator. And if that cancels out, you have yourself a whole. However, if one of them won't cancel out, then you have yourself a vertical asymptote. So you start with the denominator. That's where you're trying to find out where are the holes, the breaks, the asymptotes. And then you use that numerator to figure out, is it going to cancel out here? And if it does, then it's going to be a hole. So this says, does this rule fit for what we found in example 5? Well, back up in example 5, these were the two that we just talked about, and I already wrote this down up above. It fits because that was a removable hole. That was the last graph that we had over on the right-hand side. While as this one, there is no way to cancel this. You can't do that. So if it's not going to cancel out, it's a vertical asymptote. If it does, it's a hole. Now, example 5 says, find the domain of each of the following, then find the discontinuities of each of the following functions and classify each as a hole or a vertical asymptote. So, let's factor in. Because if we want to find all this good stuff, we need to factor. But we also need to stop right away and say, this has division. So there's a number that's out. What number is up? 2. So the domain of f, I'm just going to use interval notation this time, would be negative infinity to 2, jump over it, 2 to infinity. I'm not going to do the set over notation. But I need to factor so that I can see what's going on. So 2x squared minus 5x plus 2, there's no greatest common factor to take out of there. It's not a perfect square. We know that it has to be 2x and x. And because the last number that we see here, the positive 2 is there, but the middle term is negative, they're going to both have to be negative. So we only have got a 50-50 chance of hitting it right off the bat. We only have -1 and -2 to put in there. But to get to 5, we would need -4 minus 1. So now what we're supposed to do is algebraically, because it said find the domain of each of the following, then find the discontinuities of each of the following functions. It didn't say graph it. Algebraically, let's find it. So, is it going to cancel or not? So this is discontinuous at x equals 2. But if it's going to cancel, it's a hole. And that makes it a removable discontinuity. I think we answered every question they want. Find the domain, do that. Find the discontinuities of each of the following functions. Classify each as a whole or vertical asymptote. Do a little extra. Tell them it was removable right there. All right. Next one. What you do is you literally do the canceling, and then you take that 2 and you put it in there, and you see what you get. So the y value will be 2 times 2 is 4, and 4 minus 1 is 3. So your whole will be at 2, 3. All right, B. Well, we've got an x minus 2 down there again. So that means we're going to have our same domain. I'm going to have trouble putting this on here to keep writing so big. There's our domain. Different numerator. So let's see if we can get that factored. So again, not a greatest common monomial factor we can take out of there, and there's nothing special about this one. But in the back this time we have a -2, and in the middle we need a +3. So we're going to have to use a combination of plus and minus here. So this would be plus 4x and minus 1x. So it is discontinuous. Discontinuous at x equals 2. But if it's not going to cancel, it's not removable. What does that mean it is? It's a vertical asymptote.
What do we know if it's a jump?
We would be looking for those, Hannah, graphically, because you have not experienced those algebraic. Usually that happens with piecewise functions, so hang in there if you get piecewise things. So there's that one, and now, like I said, I wrote way too big, so maybe I could copy and paste this bugger. Come on, wake up, smart board, there we go. I'm gonna cheat. All right. This has a little bit more going on. Not sure whether or not the top is factorable yet. We'll think about that in a second. But our focus is on that difference of two squares that we see down there. The x plus 2 and the x minus 2. Because that's going to tell us right away what we have to focus on. So with this one, what two numbers are out? Positive and negative 2. All right, so our domain of t is going to be from negative infinity to negative 2. We're going to have to jump over it. Negative 2 to 2. Jump over it. And go on. So right now, I don't know if there are vertical asymptotes at both negative 2 and 2, or if one of those is a whole, or what. So I have to go back and factor that numerator so that I can see that. So x squared minus 4x minus 12. No greatest common monomial factor. It's not a perfect square. I'm just looking for two numbers that multiply to negative 12 and add to negative 4. What are they? Well, that means this is a 50-50 split. One of them's a whole, but one's not. So what we want to do is say, well, where is that hole? Which one of those is going to be a hole? The negative 2. That's the one that's going to cancel. So we'll have a hole at x equals negative 2. Where's our vertical asymptote going to be then? Oops. Let me write on that part. So we've got a hole, and then we have a vertical asymptote. The hole would be removable, but the vertical asymptote won't. That'll be an infinite discontinuity. So there's our discontinuity piece right there. You know, this was stuff from Algebra 2, but we're thinking about it at a different level here. So 43210, how are you feeling about your place of discontinuity and all that? I'm feeling maybe a little bit lower. And I think that's probably because right now you're like, you can't get the visual yet, and that's because we've kind of forgotten about the hyperbolas from last year. So we'll be talking about hyperbolas again this year. Check this Wednesday. 6. Okay, we still have a little time. Woo! All right. So, as Hannah asked about earlier, we have to see, when do we see those jump discontinuities? And usually that's with a piecewise function. So it says graph the following piecewise functions, state the domain, and classify any discontinuities. Verify by graphing on the calculator. I'm not even going to bother with that. Graphing piecewise functions on the graphing calculator is a bear, and you will never remember it, even if I teach it to you. So what we want to do is graph these. Yeah.
I don't know if piecewise functions.
How many of you remember in Algebra 2 last year, we took like 2 days and did piecewise functions? Be honest with me. Not happening, huh? Okay, well then we're all starting at the same place anyway. So piecewise functions, what they do is they split a graph into pieces. That's why it's called piecewise. And the first thing we want to pay attention to is, where is that split? And that's found right here. Those little conditionals. What that's telling me is, when x equals 0, there are changes being made other side of this graph. So I'm just going to put a little helper line here. Remember, helper lines are dashed or dotted. They're never solid. Solid means it's part of your answer. Because that reminds me that something is going on one side of this graph, but something totally different is going on the other side of the graph. So then I want to figure out, well, which one's going where? Well, this says when x is less than or equal to 0, and that's over here on the left-hand side. I'm supposed to graph x minus 1. That's what I'm supposed to graph over there. And when x is greater than 0, which is over here, I'm supposed to graph x squared. Now we could make tables, but I'm hoping we don't make tables, because if we look at this, we should say, well, this is just a line. X minus 1, I know how to graph the lines. Go down to -1, and then the slope is 1, so I'd go up 1 and over 1. But I can't go up 1 and over 1, because then I'm where x squared is supposed to be. So I'm going to use the slope backwards and say, well, normally I'd go up 1 and over 1. I'm going to go down 1 and back 1. And just use that slope backwards, because this is supposed to be a line. But then I have to stop and figure out what's happening right where this divides. And because this has an equals bar for this side, it is contained as part of this graph. And we are really going to over-exaggerate a great big dot right there to show, okay, this is a filled dot that is included. Chandler, I'm going to make that big one. Other side, x squared. Do you remember what that looks like? Y equals x squared. What does it look like? Draw it in the air for me. What does y equal x squared look like? Good. Now you may have forgotten what the parent function is, but it'll come back to you with time. Because you just put some numbers in real quick in your head. Oh yeah, that's 0, 0, 1, 1, 2, 4. So 0, 0, 1, 1, 2, 4, 3, 9. Doesn't take you long to get those. And you realize, all right, so this is going to be like half a parabola right there. But the last step again is, what do I do where this was divided? Well, this didn't have an equals bar. It just said x is greater than 0. So I have to really over-exaggerate a great big open dot for that one. Great big open dot. So now, the instruction said, graph the following piecewise functions. Ta-da! There it is. State the domain. Okay. Well, we are using all the x's and y's. We did use them all. So the domain of f, negative infinity to infinity. Classify any discontinuities. Well, we have an issue right here where x equals 0. That's our discontinuity. Discontinuous at x equals 0. And by classify, they mean give it a name. That's not a hole this time, is it? Because here we are down here at -1, and then this is at 0 up here. So this is a jump discontinuity. And then, is that going to be removable or unremovable? Can we remove jump discontinuities? So this is non-removable. So by classify, they're saying, talk to us about all the vocab that you've learned about these things. You know, and we know it's non-removable, but what more can you tell us about it? Well, we can also tell you there's a jump, and it's at x equals 0. And there's nothing we can do about it. It is just discontinuous. That's how it works. So there's our first little piecewise graph. We could get B graphed, but then we'd have to stop anyway. So we will stop there. I'll get you thinking a little bit about the piecewise. So now you can go back and finish 1 through day 1, 17 through 20, because we talked about the range. But I have absolutely no guarantee that you're going to be able to do much of day 2. But write it down. And yeah, it says extra worksheet, but we're going to save that. Probably Friday. We'll do that. looked at it this morning, we thought, 3 days, I don't think we've covered this one in 3 days. And there have been some times when this has taken us 5 days. So, just wanna make sure everybody's getting all the pieces that they need. Do what you can with the homework every day. I do expect to get 1 2-day